In covering the reactions to prepare aldehydes and ketones, let's begin by reviewing some of the reactions we should be familiar with already. For example, one of the ways we can make an aldehyde or a ketone is by oxidizing an alcohol. If we oxidize a secondary alcohol, as shown in this example, with some sort of chromic acid, so we can use chromium trioxide or we can use sodium dichromate mixed in with sulfuric acid and water will make chromic acid. That will lead to oxidizing a secondary alcohol into a ketone. We can do the same thing with PCC as well. When it comes to aldehydes, one of the most common ways to make aldehydes is by oxidizing primary alcohols. We would typically use PCC or pyridinium chlorochromate to do this oxidation. You might recall that if we try the same thing with chromic acid, we would typically, instead of an aldehyde, instead obtain a carboxylic acid. There's a molecule in biological systems that is called NAD+. This is a natural oxidant that will often be used by cells to oxidize alcohols into ketones and aldehydes. We can use the reduced version of this coenzyme called NADH as a reductant, which will do the reverse reaction and it will take an aldehyde or a ketone and convert it into an alcohol. The Krebs cycle or the citric acid cycle is a very important metabolism pathway in eukaryotic cells that converts pyruvate into CO2, ATP, NADH, amino acids, lipids, and nucleotides, among other molecules. Pyruvate is in itself a breakdown product of glucose. Here in this cycle, we can see several occasions where NAD plus and NADH are involved in oxidation and reduction reactions. For example, in this last step here, we have malonate being oxidized. So in particular, this alcohol here on the second carbon from the bottom is oxidized into a ketone through NAD+. Method to make aldehydes and ketones is through a reaction we saw previously, the hydroboration of alkynes. If we have a terminal alkyne and we add borane, hydrogen peroxide, and base, we can oxidize the alkyne into an aldehyde. Notice the aldehyde will have the same number of carbons. So here to begin with, we have 1, 2, 3, 4, and 5 carbons, and the product will have also 5 carbons. You can think of this oxidation as adding an oxygen or an alcohol at the terminal carbon. We typically expect this from hydroboration. We typically will have a anti-Markovnikov addition that will give us a double bond and an alcohol, which is called an enol, and that intermediate always is converted very rapidly into an aldehyde. If we have a terminal alkyne and again we do a hydroboration, we'll end up with an aldehyde. However, when we use an internal alkyne and we do a hydroboration, we'll always get a mixture of two ketones, since it is just as likely that we'll add the carbonyl to the right carbon or the left carbon when there are two similarly sized alkyl groups on each end of the alkyne. So in about approximately 50-50%, we'll obtain these two ketones. Also look at the mechanism of this reaction. It starts off with the alkyne attacking the boron. So when you have a boron with 3 groups attached to it, That boron only has 6 valence shell electrons around it, so 2 from each bond. And as most atoms, it prefers to have 8 valence shell electrons, so it is a great Lewis acid and can accept electrons such as those from the pi bond of the alkyne. So the alkyne is a nucleophile, it will attack the electrophilic boron. Once that addition occurs, that puts a formal negative charge on the boron, and that negative charge will actually spread out to the 3 hydrogens, since hydrogen is more electronegative than boron. So that makes these hydrogens sort of like a hydride and nucleophilic as a result. So one of these hydrogens will be added to the developing partial positive charge on this carbon, on the internal carbon of the alkyne. So you can think of that carbon as sort of becoming a carbocation. And so as a result of this addition, the boron will add to the least substituted carbon, and the hydrogen from the borane will add to the more substituted carbon. They're generally added from the same side, so this is a syn addition. The boron typically will end up on the least substituted carbon since there's less sterics there, and BH2 is a bigger group. And the hydrogen will typically be added to the more substituted carbon of the alkyne, since that is where we're going to have more of a partial positive charge compared to the any charge that would develop here. The next step would be a oxidation of this BH2 group and conversion into an alcohol. This is not a mechanism we typically cover. The result of this next step is an enol, which you can see highlighted here in sort of a pinkish color. We have an alcohol on the same carbon as this double bond. So that is what we refer to as enols, which we'll cover in much more detail later on. But enols are always in equilibrium with a carbonyl. They're called tautomers of each other, and they undergo a tautomerization. The the way you can think about enols and keto forms are essentially that these are rapidly interconverting constitutional isomers. So if we count the number of atoms in these two compounds, you'll notice that they are exactly the same type and number. So for example, there's 1 oxygen. There are 3 carbons in both. And if you count the hydrogens, you'll find that they're the same as well. So this is always true between an enol and a keto form. They are constitutional isomers of each other's by definition. And they're always rapidly interconverting, and so that's what makes them tautomers. There are other examples of tautomers, which we'll discuss later in the course, but this is probably the most common type, an enol and a keto form. Notice the equilibrium is always favored towards the keto form in not always, but in most cases. And so whenever we get in a mechanism an enol form, it usually interconverts into the keto form. Another reaction that we covered previously is the conversion of an alkyne into a ketone through oxymercuration. So if we take a terminal alkyne and we add mercury sulfate, sulfuric acid, and water, we can obtain a ketone. Notice the ketone or the carbonyl will always be added to the more substituted carbon of the alkyne. So in this terminal alkyne, it will be the second carbon. However, if we start with an internal alkyne, there is not much of a difference between the carbon on the right and the carbon on the left, even if the two have different size alkyl groups. For the most part, they won't be enough of a difference. And as a result of oxymercuration, we'll end up with 2 different ketones, resulting from adding the carbonyl on on the left side or the right side. So in this case, there's actually no carbon that is more substituted per se, and so we end up with these two ketones. Notice this is very similar to the hydroboration of internal alkynes. We end up with two ketones. With terminal alkynes, whether it's through oxymercuration or hydroboration, you can get a single carbonyl. In the case of hydroboration, we end up with an aldehyde. In the case of oxymercuration, we'd end up with a ketone. Here's another example of oxymercuration of a terminal alkyne. As you can see by this example, we have a 3-carbon alkyne, so we end up with a 3-carbon ketone. The ketone will be added on the second carbon, and so we end up with this ketone, acetone to be exact, on the right side. Here's a look at the mechanism for this reaction, covering some parts, at least the most important parts of the mechanism. The reaction starts by the nucleophilic alkyne attacking the mercury. So the alkyne has pi electrons, so it's a good nucleophile. Mercury is it's going to have a partial positive charge since it's bound to sulfates. Just the fact that it's a sort of a metal also makes it electrophilic, and so it is attacked by the alkyne. At the same time, the d orbital electrons on this mercury will start to attack the developing positive charge here on this carbon, the more substituted carbon of the alkyne. And so we end up with sort of a 3-member ring, which we call a mercurium ion. We certainly ended up with these mercurium ions when we do a oxymercuration of an alkene. But in the case of an alkyne, due to the fact that we still have a double bond, that 3-member ring doesn't really want to form. So we often draw the mercurium ions sort of in this fashion, where the mercury is bound on the less substituted carbon, and then it has sort of a partial bond, to the more substituted carbon, which has a positive charge. The water will then attack the more substituted carbon where there is a large positive charge there, and we get the Markovnikov addition of water. So the alcohol, or the water, will be on the more substituted carbon of what used to be the alkyne, and then the less substituted carbon will have the mercury sulfate. We will then remove one of the hydrogens on this water molecule that just added through using another water molecule or some other base in the reaction. It will pick up that proton, put the electrons from this bond between oxygen and hydrogen, put those electrons into this oxygen to get rid of the positive charge, and so we have now an alcohol that is bound to this double bond. Then sulfuric acid and water will convert mercury sulfate into a hydrogen through a mechanism we're not going to go into. And then we finally get to this last intermediate, which we call an enol. Notice, as highlighted here, we have an OH bound to a double bonded carbon. So that's what we refer to as an enol. And as we learned previously, enols are always in equilibrium with a keto form. So wherever the oxygen is bonded to, that carbon will become a double bond in the keto form. And then this double bond will become a single bond. And so we have acetone as a product from this reaction. When we cover the reactions to make alcohols, one of the reactions we talked about was the reduction of esters into primary alcohols. We can do this reaction as shown here with lithium aluminum hydride. So this involves the addition of 2 hydrides to this ester to make a primary alcohol. So initially, the hydride will attack the carbonyl, and then once the carbonyl is reformed by expelling this OCH3 or the methoxy group, we end up with an aldehyde intermediate. That aldehyde intermediate is reduced again with lithium aluminum hydride into this primary alcohol. If we want to stop the reduction at the aldehyde, the intermediate that we talked about in the reaction above, one way to do this is through another hydride reagent called Dibol. Dibol is an acronym for diisobutyl aluminum hydride. We sometimes refer to this intermediate as Dibol or Dibald H. So this is a hydride reagent that is sort of specialized to reduce esters into aldehydes. As we'll see in the next slide, the mechanism first starts with the dibol binding to the carbonyl oxygen. Dibol reduction of esters typically is done at fairly low temperatures. So one of the most common temperatures that we use is negative 78 degrees Celsius. Now you might wonder why 78 degrees Celsius, negative 78 degrees Celsius, what is so special about that temperature? Well, it turns out it's not really that exact temperature makes this reaction occur. It is just that it's a practical temperature to work with, since mixing CO2 and acetone makes or gives you a solution that is exactly at that temperature. So we refer to this as a dry ice bath. So it allows us to cool reactions to close to negative 80 degrees Celsius. So that turns out to be a low temperature that we need in order to make this reaction occur. Here is one more example of an ester being reduced into the corresponding aldehyde. Notice the same two carbons in the ester will be part of the product, and then this methoxy group is expelled as a methanol byproduct. Here's a look at the mechanism of a dibol reduction of an ester using the previous example on the top. So the reaction typically starts by the carbonyl oxygen attacking the aluminum. The reason for this is we have lone pairs on this oxygen, which makes it a base, a Lewis base. Note that this oxygen also has lone pairs, so it's also a Lewis base, but this is more basic. This carbonyl oxygen is more basic, since we could use the lone pair from this oxygen to push electron density through this double bond into this oxygen, so there's more of a partial negative charge on this oxygen. And so carbonyl oxygens generally tend to be more basic, more nucleophilic than other sp3 oxygens near it, such as the one that we see here from this ester. The reason why this carbonyl attacks the aluminum is because aluminum is a Lewis acid. So anytime you have aluminum or boron with three groups surrounding it, we're going to have a Lewis acid. So if an aluminum atom has three groups, that means that aluminum has 6 valence shell electrons around the aluminum. And so it wants to pick up 2 more electrons to have a full octet. So we can do that by accepting a lone pair from this oxygen to make this intermediate here, which is a Lewis acid base adduct. The oxygen will now have a positive charge. The aluminum will have a formal negative charge. They're bound to each other. That now activates this hydrogen on the dibol to be a hydride reagent. So the formal negative charge on the aluminum means we're going to transfer some of that negative charge and most of it to this hydrogen, since hydrogen is more electronegative than aluminum. That places a partial negative charge on this hydrogen. It allows it to behave like a hydride, and so it's going to attack the carbon of the carbonyl of this ester. So there is now a partial positive charge on this carbon because there's a formal charge on the oxygen, and oxygen is more electronegative than carbon, so we prefer to have the positive charge on the carbon. So even though formally there's a positive charge on the oxygen, this molecule, this intermediate, behaves as if we had the charge on the carbon, and the hydride will attack the carbon and then break the double bond to give us our next intermediate. Now notice dibol is slightly different than other hydride reagents we talked about, like lithium and aluminum hydride and sodium borohydride. So those reagents, in the case of lithium aluminum hydride, had an aluminum atom that had four hydrogens around it. So this is the structure of lithium aluminum hydride. It has aluminum in the middle. It has four hydrogens around it, and then there's a lithium somewhere around it with a positive charge. This aluminum, because it has four groups around it, has a formal negative charge. Dibol, to begin with, as shown here in the beginning, only has three groups, so there is no formal negative charge on this aluminum. Once it binds to the ester, it picks up that negative charge. So now this starts to look more like lithium aluminum hydride. This is already set up to be a hydride reagent from the beginning. Dibol, unlike lithium aluminum hydride, has to first bind to the carbonyl oxygen before it behaves like a hydride reagent. So that's the part of the reason why these two reagents behave differently. Now, under the low temperatures that we're using for the reaction, we're going to get this intermediate that is going to be very stable at that temperature. So the aluminum, after the hydride has been delivered, will be bound to both oxygens and sort of hold that intermediate in place so that it doesn't break down and eliminate the leaving group. Once we start to warm up the reaction, in other words, once we're done with the reaction, we now start to break down this intermediate. So by allowing this intermediate to now warm up with aqueous acid, we can now eliminate the leaving group, the methoxy group, and end up with an aldehyde and also methanol byproduct. So as a result, dibol will only reduce an ester into an aldehyde, while if we did it with lithium aluminum hydride at room temperature, we typically obtain an alcohol in that case because of the continuing reduction of this aldehyde with lithium aluminum hydride. Another method to make aldehydes and ketones, specifically ketones, is by using a reagent called the Gilman reagent. Sometimes we call it cuprate or diorgano copper reagents or lithium dialkyl copper reagents. So there are many names for it. And before we get into the reactions of using a Gilman reagent to make a ketone, let's first talk about how these Gilman reagents are made. So this is a reaction that is typically covered in Organic Chemistry 1, but let's review the reaction. If we take an organolithium, two equivalents of an organolithium, and we add copper iodide, we can make a Gilman reagent, which is lithium next to a copper that has two alpha groups. A byproduct of this reaction is lithium iodide. One of the reactions that Gilman reagents do is they transfer an alkyl group to certain alkyl halides. So for example, this vinyl alkyl halide, the bromine will be replaced by a methyl group from the Gilman reagent to give us this product here. We'll also obtain a byproduct of copper or methyl copper, as well as lithium bromide. Another reaction that is very similar to what we saw in the previous slide is that we can, instead of an alkyl halide or a vinyl halide, we can start with a acid chloride and replace the halogen with the alkyl group on the Gilman reagent. So here we see an example of a acid chloride reacting with this Gilman reagent, and an ethyl group will be replacing the chlorine. In this next example, we have a propyl group on the Gilman reagent, and that will replace the acid chloride, in particular the chloride from the reactant. Notice that Gilman reagents do not add to any other carbonyls, so they will not add to an ester, for example, or an amide or carboxylic acid to give us ketones or any other product for that matter.